Hello everyone. In this video we're going to be solving a nice differential equation. dy over dx equals cosine of x plus y, and we're going to be solving for y. I'll be presenting two methods, but before we get into the two methods, let's go ahead and do a little bit of substitution. So we can go ahead and write this as y prime equals cosine of x plus y. Y prime means the derivative of y with respect to x. Now at this point, since we have the sum x plus y, this is not a separable differential equation, but we can make it separable by using the following substitution. Let's call this x plus y z. I mean, you can use any variable, but I like z. So z equals x plus y. Now, notice that y is a function of x, y depends on x. When you add x to it, it just becomes another function of x. So z is a function of x, so we can differentiate both sides with respect to x. And let's use the short notation first. It's going to become z prime equals the derivative of x with respect to x is 1, and the derivative of y is just y prime. Now from here, we can isolate y prime and write it as z prime minus 1. Great. We do have y prime here on the left-hand side. We can go ahead and replace that with z prime minus 1. So the idea is to get rid of y completely and write the equation in terms of z and x if needed. Y prime let's replace with z prime minus 1, and cosine of x plus y is going to turn into cosine of z using this substitution. Make sense? Now this is an equation in z, and guess what? It's separable. It does not even have x in it, so it's really good. Let's go ahead and do the following then. Add 1 to both sides, isolate z prime, and you're going to get an amazing trigonometric expression. You'll see why it's amazing in a little bit, okay? Just hang in there. Now z prime, since I want to make this a separable equation, I already made it, but to be able to separate the variables, I'm going to write the z prime as dz over dx. Remember, we said that z is a function of x, so it can be written that way. And now, by putting the z's on the same side and the x on the other side, we can separate the variables. So write this as dz over 1 plus cosine z. So divide by 1 plus cosine z and multiply by dx, or switch these around, right? If you have something like a over b equals c, that also means a over c equals b, as long as one of these is not 0, right? Great. Now, where do we go from here? Well, we're going to need to solve for z first, so let's go ahead and integrate both sides. When you have a separable differential equation, what you can do is you have a function of z, you have a function of x, and they're separated. You can integrate both sides and then use the constant maybe on one side, and then you'll be able to relate those two variables. Make sense? Great. So the idea is then to integrate 1 over 1 plus cosine z. So this brings up an important question, right? How do we integrate this expression? So I'll be presenting two methods, as I said earlier. Let's start with the first one. So for my first method, I'm going to use is this Euler or Weierstrass? I think it's called Weierstrass substitution. Anyways, I'm going to go ahead and do the following. So my goal is to solve this integral or evaluate, right? And once I do it, I can actually set it equal to x plus c, because the integral of dx is fairly easy. It's actually x plus c. Easy, right? That part is super easy. So let's go ahead and take care of this first. And the Weierstrass substitution, it works as follows. We're going to use a very special variable, t equals tangent z over 2. Obviously, if you had x, I would use tangent x over 2. And sometimes people would use z instead of t, but since we have a z, we can't use that again. Now, this has a lot of implications. First of all, I can actually inverse tan both sides, and tan inverse is basically arctangent, right? So arctan t is going to be z over 2. So from here, z is just going to be 2 times arctangent t. In case you don't know what arctangent is, because a lot of countries will use this notation, you can also go with the tan inverse notation. This doesn't mean 1 over tangent because it's cotangent. It just means the functional inverse, okay? But z equals that, nice. And then from here, we're gonna find dz, right? What is dz? dz means you're gonna differentiate it with respect to t, which is gonna be 2 over 1 plus t squared, and you're gonna multiply by dt, so I can kind of write it as 2 dt over 1 plus t squared. Let's save it because we're gonna use it in our expression. Notice that we have a dz here. The next thing we need to do is replace cosine z with something under this substitution. Obviously, this gives us something to work with, but we need to find cosine z in terms of t. Make sense? Okay, let's find it. To be able to find that, first, we're going to find tangent z, because from tangent z over 2, how do you go to tangent z? It is the half angle, or I guess you could call it double angle, right? So tangent z from here is going to be 2t over 1 minus t squared. Because if you think about it, tangent 2 alpha is 2 tan alpha divided by 1 minus tangent squared alpha. In this case, t is tangent alpha, which I call z over 2. Okay? Make sense? Cool, cool. Now, this is tangent z. How am I going to find cosine z from tangent z? Well, you can use some identities like tangent squared plus 1 is secant squared, and then 1 over secant squared is cosine squared. That's too hard. Let's just draw a right triangle. That's the right way to do it. And then this is going to be z. Since tangent z is 2t over 1 minus t squared, 2t or not 2t, by the way, if you're a tutor, then we're basically going to find the hypotenuse. If you use the Pythagorean theorem to keep a long story short, it's going to be 1 plus t squared. Think about it. You'll get it real quick. Now, the cosine is adjacent over hypotenuse. So from here, cosine z is going to be 1 minus t squared over 1 plus t squared. A lot of times people are just going to memorize these identities like sine z, but I don't think that's necessary. Draw a right triangle. The only thing you need to know is this one, tangent z over 2 equals t, and then you can just go pretty much everywhere from there. Okay, as long as you have a little bit of trigonometry knowledge, a little bit, maybe more than that. So now we got cosine z, but we do have 1 over 1 plus cosine z. So what is 1 over 1 plus cosine z? Let's go ahead and evaluate that. It's going to be 1 over 1 plus 1 minus t squared over 1 plus t squared. If you make a common denominator, it's going to be 1 plus t squared plus 1 minus t squared divided by 1 plus t squared. The t squared cancels out, leaving us with 2 over 1 plus t squared, but that's the reciprocal. So this is just going to be 1 plus t squared divided by 2. So that's my 1 over 1 plus cosine z. Now remember, we were supposed to integrate this expression, right? But we also have dz. So we're going to replace the 1 over 1 plus cosine z with 1 plus t squared over 2. And what is dz equal to? Remember that? 2 dt over 1 plus t squared. And that's just awesome. Take a look. Everything will cancel out except for dt. Of course, if you cancel out dt, you're not going to have anything of like, what is this? Doesn't mean anything. You have to have a d something, right? Okay, so we are just going to integrate dt then, and that's just t. Think about it. It's 1 dt. 1 is the derivative of what with respect to t? It's just t. And then, of course, we're going to add the constant on the right-hand side. But guess what? T is tangent z over 2. So this integral is tangent z over 2. Again, I'm not using the constant because I'll use it later. So this integral is just tangent z over 2. And on the right-hand side, if you remember, we had a x plus c, right? So we're going to set this equal to x plus c. And then we can go ahead and do the arctangent again. If you arctangent both sides, you're going to get z over 2 equals arctan or tan inverse, whichever you like, is going to be this. And multiply both sides by 2, and you're going to get the answer. But of course, you still need to back substitute because z is x plus y, but that's easy. That part is the easiest thing. Don't you love it? At the end of a problem, you've done so much work, and this is the easiest part. And you can kind of isolate y from here and write this as 2 arctan x plus a constant minus x. Obviously, we're not adding a constant here because we already added, so we're all good. And that will be the solution basically. But of course, we kind of have to consider different cases. But let me go ahead and introduce the second method real quick, and then we're going to look at the results from Wolfram alpha. All right, ready for the second method? Because the second method is just awesome. And second method basically depends on, so by the way, why did this work so nicely and we ended up with something as simple as dt? Because this is probably how the Weierstrass substitution came about, right? Because it was mainly designed for something like this. Perfect fit. Now, we're going to use the double angle formula. Do you remember cosine z can be written as 2 cosine squared? If you had cosine 2 alpha, you could write 2 cosine squared alpha minus 1. But in this case, half of that will be z over 2 minus 1. And guess what? The negative 1 and the positive 1 cancel out, leaving us with something nice. That's why this is nice. 1 cancels out, and we get 1/2 of secant squared, because this is just secant squared, z over 2. And that's kind of nice, because if you think about the chain rule and the derivative of z over 2, you're going to get 1/2. So 1/2 is already there, so we're all good. What is the integral of secant squared? If you think about it, the derivative of tangent is secant squared, and 1/2 will be taken care of by z halves, plus the constant, of course, right? Wait a minute, we're not going to use the constant, so never mind. So now this is the same as before, so you're going to end up with the exact same solution. Let's go ahead and take a look at Wolfram alpha, but you see, the second method is hopefully much better, right? Don't you think? And here's the result. Why did Wolfram alpha give us 2 different results? That's for you to find out. That's your homework. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.